Imagine that you are standing on the edge of an endless ocean, the glittering space reflected in its waters. Now imagine that this panorama, with its multitude of stars and swirling galaxies, is a reflection, a projection, from an invisible distant shore. This is not the beginning of a fantasy tale, but a look at one of the most amazing theories in modern physics. The holographic principle is that just as each droplet in a spider's web represents the world in miniature, our universe can be a large-scale representation of the fundamental laws written on distant horizons. Far from the solid ground beneath our feet and the void of space, the fabric of our reality may be formed by something much deeper, something beyond our present understanding. Let's continue this search together and try to answer the main question. Does the fabric of our universe originate from a holographic edge? At the heart of physics is discovery, peeling back the layers of reality to reveal its basic elements. These elements, called ontological primitives, are the general structure of the universe. For centuries, physicists have searched for these building blocks in their quest to understand the laws of relativity. The journey begins with the concept of space. Isaac Newton, one of the titans of science, envisioned space as an absolute, immutable background, indifferent to the comings and goings of matter and energy. For Newton, space was an absolute perception, an infinite expanse in which all the events of the universe played out. However, as our understanding deepened, this view of space began to evolve. The emergence of Einstein's theory of relativity painted a different picture, where space was not just a passive arena, but an active participant in cosmic interactions. According to the new view, space can be bent and bent in the presence of mass and energy, challenging the notion of its absoluteness. A holographic principle emerges between the changing perspectives. This principle suggests that our three-dimensional perception of the universe may resemble a hologram, a projection from a two-dimensional surface located at the edge of space. This field, though infinitely distant and inaccessible to direct observation, contains the basic information that creates everything we perceive as reality. This concept overturns our conventional notions by arguing that space is the essence, the fabric of our reality. May not be a fundamental characteristic of the universe, but it emerges. Emergentism describes phenomena that arise from the complex interaction of simple elements, resulting in new, invisible properties and order based on new components. In the context of our universe, and especially within the holographic principle, emergentism plays an interesting role. Here, the term refers to the fact that the three-dimensional space we travel through and the time we experience are not the basic blocks of reality. Instead, they emerge from a basic or two-dimensional structure, a holographic boundary that encodes the information and laws that create our perceived reality. In this grid, every star, planet, and galaxy is the manifestation of physics, from the laws of gravity to electromagnetism and the fabric of space. It acts as a bridge between the known and the unknown, the observable dimensions of our universe and the underlying encoding of reality in the holographic realm. It invites us to rethink not only the structure of the cosmos, but the nature of reality with the layers of the universe. Against the background of our hypothesis, black holes, where gravity prevails and even light cannot escape, have become unexpected heroes thanks to the pioneering views of Stephen Hawking and Jacob Bekenstein. Hawking and Bekenstein ventured into uncharted territory by attempting to combine the fields of quantum mechanics and general relativity to study the thermodynamics of black holes. Their theories revealed the surprising fact that black facts are not absolute points of entropy, but play a fundamental role in the cosmic interaction of information and energy. Entropy is usually associated with disorder in a system that has taken on a new direction. a veil formed inside the black hole, hiding the information. It was not just about the randomness or disorder of particles, but about the hidden layers of information that define the structure of reality. When spiraling matter enters a black hole, it seems to disappear from our universe, which raises a big question: what happens to the information it carries? This question focuses on entropy, not only as a measure of disorder, but as a key to understanding the fate of input data. As Bekenstein suggests, the entropy of a black hole is not directly proportional to its size, but to a concept that defies our everyday understanding of physical laws. This connection between surface and entropy leads us to a profound conclusion. The maximum amount of information available in any region of space is determined not by its volume, as one might intuitively think, but by its surface area. This vision laid the foundation for the holographic principle, which postulates that all information of a volume can, in principle, be encoded on a two-dimensional surface. Thus, Hawking and Bekenstein's discovery of black hole thermodynamics suggests a universe in which the fabric of reality, every particle, every force, and every dimension of space and time may be features emerging from a deep two-dimensional fabric. At the forefront of bridging the gap between the mysteries of black hole thermodynamics and the holographic principle is Juan Maldacena. This piece is not just a frame, but a concrete example of holographic principles. Maldacena's correspondence asserts a duality between the so-called anti-de Sitter space, abbreviated ADS, and conformal field theory, or CFT, which exists at the boundaries of this space. Despite the positive cosmological constant of the universe, in contrast to the negative constant of the ADS space, principles derived from this duality help us understand the nature of gravity and quantum mechanics, and by extension, the holographic nature of our universe. Central to this dualism is conformal field theory, which operates at the boundary of the universe within ADS CFT. CFT is unique in its scope and diversity. The laws governing these field theories remain the same regardless of size or scale. This characteristic of the CFT is key because it encodes the information needed to describe a high-dimensional bulk area in a low-dimensional frame, effectively representing the waveguide principle. Within CFT, scale invariance is not only of mathematical interest, it is a window into the creation of dimensions and the fabric of space. The various patterns between the edges, governed by the uniform laws of CFT, contribute to the illusion of three-dimensional space. This view emphasizes the holographic principle that the complexity and dimensions of a volume's space arise from finitely simple, scale-invariant dynamics. Through the prism of ADS-CFT and the content of conformal field theory, we gain a deeper understanding of how dimensions and the structure of space-time arise. Scale and variant boundaries each contribute to the holographic encoding of the universe. One of the most obvious metaphors for this complex idea is the concept of nested spheres. These nested areas serve as a visual framework, with each layer representing different scales of different border patterns. The best samples are densely packed with information, similar to the microscopic level, and require high-resolution understanding. When moving to finer areas, the samples gather the same information, but in a more generalized, less detailed form. The patterns in the microscopic space of the holographic border are dense and highly detailed, resembling the fine strokes of a master artist. These fine-grained patterns are the most basic level of the universe, where every tiny element is packed with information that encodes the laws of physics and the initial conditions of cosmic phenomena. The transition from the micro to the macro environment is like a mosaic. Up close, we see only individual tiles, each with its own color and shape. But from a distance, a complex and overall image emerges. Likewise, the larger structure of the universe, galaxies, stars, and planets emerges from this collective arrangement of fundamental patterns encoded in the holographic boundary. The transition to fine-grained patterns at the boundary of the universe is not only a feature of the holographic model, it is a fundamental process that shapes our perception of space. This highlights the differences in information requirements at different scales by displaying advertisements. Suitability and efficiency of space, holographic coding. The concept of the holographic universe is based on deep philosophical and scientific concepts, ontological democracy. This idea suggests that the boundaries of the universe, its two-dimensional information encoding, and the three-dimensional space we are familiar with, may be the same basis for the fabric of reality. Neither is more real or fundamental than the other. Rather, they coexist in a state of mutual emergence. This view has far-reaching consequences. What we perceive as the three-dimensional reality of stars, galaxies, and planets, with their complex interactions, may be a reflection of deeper, fundamental laws encoded in the far and visible. This encoding not only shapes the structure of the volume, but also the events within it, creating a reverse cycle. In our journey through the holographic universe, we encounter the profound reflection of gravity, which is traditionally thought of as the curvature of space-time under the motion of mass. In holographic terms, gravity arises not from mass itself, but from entropic forces acting on information encoded at the edge of the universe. The idea that gravity can be an emergent phenomenon, like temperature or pressure in thermodynamics, represents a radical change in perspective. What we perceive as gravitational attraction is the result of the universe's tendency to maximize entropy, an idea first proposed by physicist Erik Verlinde. This theory suggests that gravitational attraction arises from changes in the amount of information associated with the position of material bodies. The holographic universe also prompts us to explore the mysterious role of quantum entanglement in the fabric of space-time. Quantum particles remain interconnected, and the state of one particle can instantly affect the state of another, regardless of distance, which can be the thread that weaves this spatial continuum of the universe. According to this view, the cosmos itself is formed from a series of quantum bits encoded in the cosmic boundary. When particles are connected, they share a common bond that contributes to the illusion of continuous space. Theoretically, uncovering these particles could cause the space between them to disappear, challenging our notion of distance and locality in the universe. The principle of the holographic universe, of course, like any other theory of physics, raises the fundamental question of finding a universal holographic model. This ambitious endeavor is designed to unify the universe's myriad complexities into a single structure that accurately describes both the grand cosmic scale and the minutiae of quantum mechanics. The difficulties in this work are great. Creating a universal model requires not only a deep understanding of quantum mechanics and general relativity, but also a new approach to integrating these theories into a holographic framework. Potential discoveries promise to revolutionize our understanding of space. A successful universal holographic model could provide unprecedented insights into the origins of the universe, the nature of black holes, and the fundamental laws that govern reality. In examining the possibilities of this theory's limits, we may be on the verge of a new understanding of the cosmos, or the rejection of a high-profile theory. If reality is holographic, our perception, experience, and existence may be much more connected to space than we think. This journey is fraught with challenges and uncertainties, but the promise of unlocking the universe's deepest secrets compels us to search for a universal model that will define our place in space. Imagine being able to harness the power of the sun, which has been the lifeblood of our planet for billions of years. Its energy, produced in a process called fusion, lights up our world and sustains life. But what if we could replicate this process on Earth? What if we could create our own miniature suns to power our homes, cities, and world? Sounds like science fiction, doesn't it? But what if we told you that it's not a distant dream, but a bee of scientists? And approaching decades? At the Lawrence Livermore National Laboratory in Central California, a dedicated team of scientists is working tirelessly on this mission. Their purpose? Perform an atomic fusion, a feat that is changing the way energy is produced and paving the way for a future of clean, unlimited power. Recently, at the end of last year, there was a discovery that could illuminate our future and change everything. Imagine our star, the Sun, 93 million miles away in a vast expanse. It's an incredibly hot tub. Have you ever wondered what makes the Sun shine? The answer is both simple and complex: an atomic compound. In simple terms, nuclear fusion is the process by which two lighter atoms combine to form a heavier atom. It's like taking two small Lego blocks and putting them together to make a bigger one. But there is a catch. When these atoms combine, they release a lot of energy. And they emit so much energy that it allows the Sun to power and shine. Now you may be thinking, that sounds great. But what does this have to do with us on Earth? If we could repeat this process, we could create an almost limitless source of clean energy. Imagine your home, city, or even your car going through the same process as the Sun. It promises to join us. But this idea is not entirely new. Scientists have dreamed of harnessing the power of fusion for decades. In fact, the concept of nuclear fusion was first introduced in the early 20th century by physicists such as Albert Einstein and Hans Bethe. Over the years, there have been many attempts to achieve fusion, from the Sherwood project in the 1950s to the first tokamaks in the 1960s, and the construction of modern facilities such as ITER and the U.S. National Nuclear Facility. Each of these efforts came close to the goal of achieving unification. Although there were problems and setbacks along the way, the dream of harnessing star power never faded. And now, with a breakthrough at Lawrence Livermore National Laboratory, we may be closer than ever to realizing that dream. Imagine a world where the light in every house, street, and city is powered by stars, not coal or gas. As we mentioned earlier, fusion is the process by which two light atoms combine to form a heavier atom, releasing a large amount of energy. But what makes the process so special? Why are scientists all over the world interested in it? Most of our electricity today comes from burning fossil fuels like coal and gas. These processes release harmful greenhouse gases into the atmosphere and contribute to climate change. Such resources are also finite, which means they will run out sooner or later. But fusion offers a different path. Fusion produces fuel with hydrogen isotopes, deuterium and tritium. Deuterium can be extracted from seawater and tritium from lithium, which is abundant in the Earth's crust. This means that the fuel for fusion is almost infinite. And remember, the energy released by fusion is huge. 1 gram of fossil fuel can produce the same amount of energy as 8,000 gallons of gasoline. It's like walking over 300 Earths 300 times. Fusion can produce large amounts of energy in addition to the carbon emissions associated with fossil fuels. It can help us fight climate change and move into the future. The approach to fusion energy extends beyond the scientific community. Political figures, such as the United States, Senate Majority Leader Charles Schumer, also recognizes its potential. This discovery, he said, is a big leap forward in making fusion power a reality. This marks the beginning of a new era of clean and virtually limitless energy production. The potential for our economy and environment is enormous. As such, It is not surprising that the fusion race is often compared to the space race of the 20th century. But nuclear fusion is not easy to achieve. This requires incredibly high temperatures and pressures, such as in the heart of the Sun. Moreover, for many years, the energy required to initiate a fusion reaction exceeded the energy it produced. But that's where Lawrence Livermore National Laboratory and the National Ignition Facility come into play. They are working to make the merger a reality, and their latest success could be a game changer. Imagine a place where the world's brightest minds come together to solve the biggest challenges facing humanity. This place is Lawrence Livermore National Laboratory, or LLNL for short. Located in California, LLNL is a center for scientific and technological innovation. It's home to thousands of scientists, engineers, and other professionals who work on projects ranging from national security to environmental science to, you guessed it, fusion. One of LLNL's crown jewels is the National Induction Facility, or NIF. This is where the magic of fusion happens.